Hello everyone, welcome to this course on advanced quantum algorithms. This is the first lecture of this course. I am Dheeraj Madan and I will be the instructor for this course. So as the name suggests, this is an advanced course on quantum algorithms. So we are expected to have some prerequisites. So the prerequisites of this course, they include firstly some basics of quantum states, gates and quantum circuits. Secondly, you are also expected to know some basic quantum algorithms such as Bernstein-Vazirani, Deutsch-Joshua and either one of QFT or Grover's. So actually QFT and Grover's are not essential because we will review these algorithms in this course, but it will be good if you have seen some of the analysis associated with these. Now the topics which we will cover in this course, they include so firstly we'll look at some algebraic problems, some quantum algorithms for some algebraic problems. So for example, so basically these are algorithms based on some generalization of Fourier transform, which could be, so this is essentially called as group Fourier transform. So this is one area. Another is quantum walks. Thirdly, we'll have a look at some simulation algorithms, Hamiltonian simulation, and we'll also have a look at some linear algebraic algorithms. The primary reference for this course which I plan to use will be notes by Andrew Childs. So I'll put a link to these notes in the description box below, and as and when required I'll refer to recent research papers. Okay, so as far as today's lecture is concerned, today firstly we'll look at some basically review of quantum states, gates and circuits. So this is something which you are all expected to know, okay, but in today's lecture we'll just study it again to set up the notation. This is one thing. Secondly, we will also look at quantum Fourier transform, but in a recursive formulation. Okay, so let's study these. So let's do review and notation. So firstly, a state on n qubits . So a state on n qubits is represented by ket psi. So ket is the general notation for representing a vector in or a quantum state, and then this is supposed to be a unit vector in 2 to the power n dimensional space, right? For n qubits we have a 2 to the power n dimensional space, and we can of course always express it as a linear combination of basis states. And AXs, these are the coefficients associated with these basis states. In abstract form, the states may be represented by elements of a group G. Okay, so these could be superposition of elements from a group G. So we'll see, where this also makes sense. So here I can represent a state ket phi as sum over J Bg ket G. So these are the coefficients Bg's. Of course, this is always a unit normalized state. And when we refer to ket G, okay, so when we write ket G, we have a canonical bit string representation of group elements. So basically all these elements are coming from the group capital G. Now what is a quantum circuit? So a quantum circuit essentially consists of unitary operations. So what is a unitary operation? A unitary operation is one which preserves inner products, which is equivalent to saying it preserves norm, and it can also be shown that it is equivalent to showing that it maps unit vectors to unit vectors, provided it's a linear operation. Okay. Now the quantum circuit, right, which we will see in practice. So these not only should it be a unitary operation, it should be possible to efficiently realize it as a combination of single plus 2 qubit gates. Right? So what are these gates? So these could come from some universal family of gate, for example H, S, C naught and T. This is one particular family of gates. H, S and C naught, they form Clifford circuits, and Clifford plus T gives us the universal family. Okay, so now this was basic review of quantum states, gates and circuits. Now essentially let's look at quantum Fourier transform. So this was something which you were expected to know. It was more of a revision exercise. So now let's see QFT or quantum Fourier transform. So firstly, let's review the idea of classical Fourier transform. So in classical Fourier transform, we are given an input vector which is like x0 up to x capital N minus 1, where capital N is 2 to the power small n, and the output must again be a vector y0 up to y capital N minus 1. This should satisfy the condition that y sub j equals to sum over k x sub k omega n to the power of jk. Okay, and then there is a normalization 1 over root n. So we add this normalization because we want it to be a unitary operation. Here of course omega n is the nth root of unity. So homework exercise for you. Show that Fourier transform is a unitary operation, meaning that you have to show that it maps unit vectors to unit vectors. So this was how classical Fourier transform is defined, and now we'll have a look at quantum Fourier transform. So a quantum Fourier transform consists of an input state which is of the form sum over j xj ket j. The expected, this I'm going to denote by ket x. The expected output state is ket y, which is sum over j yj ket j, where y sub j is 1 over root n sum over k xk omega n to the power of jk. Okay, so essentially the thing is that we have the same sort of mapping, but now we are going to represent it in the form of these quantum states. So an observation is that, so basically this observation will enable us to get to classical fast Fourier transform, and then we'll use the same observation to derive quantum Fourier transform, a recursive formulation of quantum Fourier transform. So the observation is that, yj, if I write it as 1 over root n times sum over k xk omega n to the power jk, and I can rewrite it as 1 over root n times sum over k from 0 to n by 2 minus 1 x2k omega n to the power of 2jk plus x2k plus 1 omega n to the power of j times 2k plus 1. So what we have done over here is that we have splitted the summation over k into two set of terms. One is the set of even indices of k and other is the set of odd indices of k. Okay, so this equals 1 over root n times sum over k from n by 2 0 to n by 2 minus 1 of x2k times omega n square to the power jk plus x2k plus 1 times omega n square to the power jk times omega n to the power j. And now I can actually write capital N as n by 2 times 2. Okay, you know what's happening now. So omega n square is nothing but omega n by 2, right? Because it's e to the power iota 2 pi by capital N, and then square of that is e to the power iota 2 pi by capital N by 2. So this is also omega n sub n by 2. And now what I have over here is that essentially this summation, okay, this is now the Fourier transform of the even terms, right? And this is the Fourier transform of odd terms times omega n to the power j. So but in order to get to that, I'll also have to change this 1 over root n to 1 over root n by 2. That's why we are going to write n as n by 2 times 2, right? And this 1 over root n by 2, I'm going to let it go inside. So what I get is that 1 over root 2 times sum over k from 0 up to capital N by 2 minus 1 x2k omega n by 2 to the power jk over root n by 2 plus x2k plus 1 omega n by 2 to the power jk times omega n to the power j over again n by 2. Now this is essentially nothing but the jth term, right, of the Fourier transform, but provided we are looking at the Fourier transform of even terms, right? So okay, let's write that formally. So suppose j is lesser than n by 2, then essentially these are the Fourier coefficients of x even, which is x0, x2 up to xn minus 2, and x odd, which is nothing but x1, x3 up to xn minus 1, right, respectively. So therefore y sub j is now equal to 1 over root 2 of, okay, so this is the y sub j even, and then we have a y sub j odd. So 1 over root 2 of y sub j even plus omega n to the power j y sub j odd. This is for j less than n by 2 and for j greater than equal to n by 2 we write j as j prime plus n by 2. So therefore y sub j prime plus n by 2 equals 1 over root 2 times y sub j prime even, okay, plus omega to the power omega sub capital N to the power j prime plus n by 2 y sub j prime odd, right? Because what's happening over here is that, so if I replace j as j prime plus capital N by 2, okay, and essentially omega to the power of capital omega sub capital N by 2 to the power of, you know, n by 2k, so that will just give me identity. So I'm just you know, try it as a homework exercise. So omega sub capital N by 2 to the power of j prime plus n by 2 times k is just omega sub n by 2 to the power of j prime times k, right? Because omega sub n by 2 to the power of n by 2 times k is just identity. And the extra difference which will come up is that I have omega sub n to the power of j prime plus n by 2, but omega sub n to the power of n by 2, that will just give me minus 1. Right, so from here I am just going to get 1 over root 2 times y sub j prime even minus omega n to the power of j prime times y sub j prime odd. So essentially, if I can compute the Fourier transform of even terms separately, odd terms separately, and then I combine them as follows, I am going to get the Fourier transform of all the terms together, right? So what fast Fourier transform does, So firstly, it recursively computes y even and y odd. And secondly, it combines the results using the above expression. So the total time t of n is twice t of n by 2 plus order n. So this solves to Tn is order of n log n. Why to Tn by 2? Because you have for each of the recursive calls to even coefficients and odd coefficients, the time is t of n by 2, and then there is an order n time to combine the terms. So the total time is order of n log n. Now the way quantum Fourier transform works is that it tries to combine the two recursive steps in superposition, right? And then it performs the n conquer steps in superposition, which requires order log n time. So it performs the two recursive steps in superposition. And secondly, perform the n conquer steps in superposition. So this requires order log n steps. Okay, so now the recurrence relation is essentially t of n is t of n by 2. So note that instead of 2tn by 2 we have t of n by 2, because this requires like the two recursive steps are done in superposition, and then there is an order log n number of steps to perform the conquer step. So if you solve this recurrence, you will get Tn is order of log n squared. So let's see how it works in practice. So in practice, you have your input which is sum over j xj ket j. So this can be expressed as sum over j from 0 up to capital N by 2 minus 1 of xj0 ket j0. So what I have done is that I have splitted out the last qubit separately. So now instead of summing from 0 up to capital N minus 1, I sum j from 0 up to n by 2 minus 1. But now I have two sets of terms, the even terms and the odd terms. Right? And now the way we do it is that we apply QFT of n by 2. Basically, we apply on the first n qubits. We apply QFT. First n minus 1 qubits. Okay, so that will give me sum over k 0 up to n by 2 minus 1 of yk even k comma 0 and then yk odd k comma 1. So essentially I apply QFT on basically the first n minus 1 qubits. The last qubit is kept separately, and essentially from here I get yk even sum over k yk even ket k, and here I get sum over k yk odd ket k. This ket0 and ket1 are kept separately. Now how do I combine them, right? So as we saw, we need to basically add yk even plus omega into the power k yk odd, and similarly minus omega into the power k yk odd. So what we do is that we apply a controlled phase, and that gives me sum over k 0 up to capital N by 2 minus 1 yk even ket k0 plus omega n to the power k yk odd ket k comma 1. Now I apply Hadamard. It's a basically condition on this last qubit being 1. I have a phase of omega n to the power k. So the amount of phase is dependent on the first n minus 1 qubits, but whether to apply that phase or not, that depends on the last qubit. So the conditioning is done by the last qubit. Okay, and overall what I get is that, okay, so this is how I get it at this point, but now I have to even add and subtract terms. So what do we do? So what we do is that we apply a Hadamard gate on the last qubit. So this gives me sum over k from 0 up to capital N by 2 minus 1 of yk even plus omega nk yk odd over root 2 ket k0 sum over k from 0 up to n by 2 minus 1 of yk odd minus omega n to the power k. Wait. Okay, let's see this step by step first. What I have over here is that sum over k 0 up to capital N by 2 minus 1 yk even ket k plus omega n to the power k yk odd ket k minus. And this ket plus, I can write it as 1 by root 2 0 plus 1 by root 2 1. Similarly, ket minus is 1 by root 2 0 minus 1 by root 2 1. And now I combine the 0 terms and the 1 terms together. So overall what I get is that sum over k yk even plus omega n to the power k yk odd over root 2 times ket k0 plus yk even minus omega n to the power k yk odd by root 2 times ket k1, right? And now what I wanted was that I wanted for the terms which were greater than capital N by 2, I wanted a plus sign, and for those less than for those less than n by 2 I wanted a plus sign, and for those greater than n by 2, greater than equal to n by 2, I wanted a minus sign. So essentially this looks correct, but essentially this ket0 and ket1 should have been in the most significant bit instead of least significant bit. So what we can do is that, well, either we perform this swap every time with the sort of the basically we take this ket0 to the initial bit every time, which will require probably more swaps. But then what we can do is that we can just run this algorithm and pretend that in the output the MSB is the LSB. So basically we just run this algorithm, and then in the end we can do a swaps together. That's something you can do. So recursively how the circuit now looks like is that if I have to do a QFT on, let's say, on capital N, then essentially, you know, this is going to have, let's say, qubits which are indexed by 0, 1, 2, 3 up to n minus 1. So I'll take the first n minus 1 qubits, which is that, you know, 0 up to n minus 2. I apply QFT sub capital N by 2, and then conditioned on the last qubit, I apply these phases. Okay. So essentially conditioned on the last qubit, I need to apply omega n to the power k, right? And omega n to the power k is nothing but e to the power iota 2 pi over 2 to the power small n, and then sum over j from 0 to n minus 2 of kj 2 to the power j, right? Which gives me e to the power iota 2 pi times k naught 2 to the power minus n plus up to k sub n minus 2 to the power of times 2 to the power of minus 1, right? So this is how this circuit is going to look like, and then in the end I can do a pairwise swap of qubits. Right, so basically the thing is that conditioned on the last qubit, I apply like for the 0th qubit I apply a phase of R2 basically. So I apply a phase of, you know, e to the power 2 pi over 2. Here I apply a phase of e to the power 2 pi over 4, and so on up to here I apply a phase of 2 pi over 2 to the power of n. Right, so here essentially r sub, let's say r sub k is essentially a phase of e to the power iota 2 pi over 2 to the power of k. Right. So essentially on the kth qubit the phase is of rk, right, which is a phase of e to the power iota 2 pi over 2 to the power k. Right. So this is how overall the circuit is going to look like, and you can see that the number of these rotation gates which I have applied is of the order of, you know, small n, and if I open up this QFT sub capital N by 2 recursively, then I'm going to get order of small n square gates, which is order of log square n, and in the end I can do a pairwise swaps, so that will sort of complete the Fourier transform, because it will change MSB to LSB as we needed. Right, so this is a recursive formulation which is slightly different from what you might have seen so far, but I assume that you have already seen this type of circuit before, so this is more of a review exercise. So thanks a lot. Bye.